Hi everyone, welcome back. Welcome back to the Q2B. It's amazing to be here once again after a couple of years that we were not here physically. And it's really great to see so many of you in person after quite some time and also see some new faces over here. So it really is a pleasure. And beyond this pleasure, I think that we are really all very, very lucky to be part of an industry while it's emerging. Right? That doesn't happen often. And not just another industry, but an industry that is possibly going to be very disruptive and very impactful, right? Quantum computing. And even though these are the very early days of quantum computing, we believe that it is now the right time to start asking, how will the computing environments in which quantum computers will be in look like? And how should we best develop them as a community in order to serve the end users of these computers for their own use cases? And taking lessons learned from other industries, such as the high-performance computing industry, we believe that these computing environments will be highly heterogeneous, namely composed of a multitude of different technologies. So let's talk about that. So let's begin first with the word, heterogeneous. So I must admit, for me, it's a terrible word. It's a terrible word for someone who is not a native English speaker like myself, as you can tell, especially if we look at some of its variations like heterogeneity, right? I'd actually need a whole weekend to practice just to say it once properly. But in our context here, what does heterogeneous mean? Heterogeneous means quite simply the combination of multiple different technologies, computing technologies, and algorithms, and simulations, and AI, and GPUs, and x86s, and quantum, of course, and FPGAs, and so on and so forth. The list goes on. Each of which handpicked for the particular capabilities that it brings to a particular use case, right? Or in simple terms, and these are, of course, not the simple terms, consisting of dissimilar or diverse ingredients or constituents. In simple terms that would be even clear for my 4-year-old son, that is something like combining different games into one bigger game. Okay, that's what we're talking about here, right? That is heterogeneous. And in fact, and this is one of the main points for today, for many talks, by the way, this is not so trivial because if you're familiar with these games, if I take, for example, a piece of Lego and I try to combine it with a piece of Mega Bloks, right? They do not combine. I put one on top of the other, it falls right off, right? So it's not very trivial. And then how would we then go about it? So maybe here's an idea. Why don't we just shove them all into a 19-inch rack, right? Maybe this is a good idea. And then connect them all to the internet, right? Of course, this is not a good idea because then I'd still take each one at a time and play with it independently, right? And this is not the right approach. Maybe the right approach, if I ask my son, I'm sure it has to involve, to some extent, Spider-Man. He loves Spider-Man, loves it very much. So what does that mean? It means that maybe in his mind, Spider-Man will then go from one castle to the other and actually take objects or variables from one castle to the other and then do whatever it does on it in each one of these castles. Maybe a different computing type, different process in each one of these castles. So maybe this is a better kind of example inspired by my son, Ari. So before we run forward to the end game of quantum computing, let's maybe just take a few steps backwards, okay, for a moment and talk about the present. Okay, so quantum computing situation assessment, where are we now in the field? So the first point is, I believe, most of the audience here is convinced, I hope, that quantum computing will ultimately be beyond Grover's algorithm and Shor's algorithm. Okay, I'm convinced. I hope you are as well. The second is that many of us have now quit the if question. If quantum computers will happen, right? If they materialize, whether they will materialize, right? And we're now much more focused on the how, right? And how is also decomposed into many different hows. So one how has to do with, again, the first bullet, which is what algorithms are we going to use? The second how is what quantum platform are we going to use, right? 3 years ago at the Q2B, we talked mostly about superconducting qubits and trapped ions. I think this year we see a lot of talks, a lot of dominance by neutral atoms. What are we going to see in 2 years or 3 years? Personally, I hope we'll see them all, but no one can tell how this will evolve. Another how goes back to the computing environment and the computing infrastructure in which quantum computers will live and thrive. And next is that we're now reaching some very important inflection points, which has to be addressed by our community, right? What are these inflection points? So we talk about moving from homegrown to commercial grade solutions. We talk about moving to scaling up, and we're talking more and more about practical quantum computing happening for real, right? So let's talk about each one of them at a time. So from homegrown to commercial grade. So what does that mean? It means that there's a certain point in an industry where commercial grade solutions are required in order to maintain the momentum. So for example, you may have a great solution with great capabilities, right? At some point in the stack, right? It has great capabilities, but is that enough? Not necessarily, because is it robust? Is it reliable? Is it deterministic? What's its uptime, right? And so on and so forth. The list goes on. So this is one. The next has to do with scale. So let's say that all of the above is true. You have a wonderful solution, and it's all of the above, but then can you make 10? Can you make 100? Can you make 1,000, right? And what's going to be the lead time, right? What's going to be, how serviceable is it going to be? If it's software, is it going to be elastic, right? And so on and so forth. Here as well, the list goes on. And the last point is really about how are we going to make these machines of practical use, right? And this, in my opinion, is the most important question, the most interesting question, because it goes beyond the standalone quantum algorithm or quantum computer, right? It goes way beyond it. And while quantum computing is very exciting and potentially very disruptive, we should humbly admit that it is not the first potentially disruptive technology, right? We have many other examples like AI, many of which were adopted in the course of time by the high-performance computing community. And there are many lessons that we can actually learn from them, and this is what we do all the time at Quantum Machines. So we wanted to talk today about a couple of them in this talk. So the first example, the first lesson learned has to do with adoption, okay? And this example begins with a rather trivial statement, which is the adoption of new technologies is driven by the need for greater capabilities, right? And the need for greater capabilities doesn't mean that there is a problem that was not solved and it's waiting for a new technology to solve it. It can be just a problem that was solved but can be solved better and better and better and better. This is what we've been, not we, but the high-performance computing community has been doing for many, many years, just improving for actually decades now, right? For some domains which are always thirsty for more and more computing power, right? And so we have a few examples here. And the way it works is that once we have a first adopter, right, he will take this machine, for example, the quantum computer, and what he will do is he will trivially create a new method, okay? And this new method, we define it, a method is defined by a way that a new technology is used for a particular use case of a particular user, right? Which is potentially of business interest, right? So a way that a new technology is used for a particular business case or use case, right? And so let's give an example, and not the example over here. Let's give the future quantum computing computer example. Let's say that in a year or two, I give someone here a 500 qubit quantum computer. And of course, I glorify it. I say all the wonderful things that it can potentially do, right? The user will take it and will explore it and will eventually find a very particular, maybe a very niche, very specific method or an algorithm that is suitable for his own use case, right? And then what is he going to do right after that? He will come back to me and he will say, Itamar, give me more of that quantum computer, right? And he will not mean give me more in general of the quantum computer. Don't just give me more qubits, but give me a newer version of that quantum computer which will better suit the use case that was addressed by this method, right? And likely, the competitor of this user will approach me as well and tell me, okay, give us that as well. Give us this new version of this technology as well. And my competitors will approach these customers and tell them, we may have an alternative technology for your specific use case. And this cycle, which we actually see for many years in several industries, and of course in high-performance computing, results in the following way. So it is possible that in 10 years from now, the technologies that we're using today, right, or how they look like, and the methods are going to be completely different, right? And this is the cycle that we have to expect, that we expect is going to happen. And the result, the iterative result of it is the methods, which is in the most cases, the algorithms, right? And the algorithms, this takes us to the second very important point that we want to make here, which has to do with integration, right? Because the algorithm is maybe the heart of the use case, but in fact, it's not the entire use case because there is a much bigger picture here. Because the algorithm is typically a part of a greater thing, which is a workflow, right? And the workflows are from one year to the next, they become increasingly heterogeneous, right? Again, including many technologies and many disciplines, right? Therefore, leading us to the main conclusion, which is that the effective and tight integration into workflows, as we know them today, is paramount to the adoption of new technologies, and of course, for quantum computing among them. And this is kind of the whole picture that we see in front of our eyes as we architect what we develop and its integration. And we have here an example that we crafted. It goes from the far past into the future, right? With a field that, of course, benefited from high-performance computing for many, many years, and that is weather forecasting, right? So weather forecasting, of course, for several decades have always been at the forefront of whatever computing components we have, x86s, GPUs, vector processors, and so on and so forth, going from single to massively distributed systems, and always pushing their limits, right? At some point, machine learning and deep learning were introduced, but at the beginning, they were actually leveraged for weather forecasting in a very standalone manner, right? Simply for the very kind of closed applications such as severe storm feature detection, right? And it was only after that that it was properly integrated, machine learning and deep learning was properly embedded into greater workflows that actually resulted in better results for weather forecasting. So what can we imagine now going to the fourth step into the future? Perhaps quantum computers will first be used in the context of weather forecasting to simulate some underlying molecular processes that are relevant in this context. And only after that, we will see a greater workflow that will include all that we've mentioned, and for which we found a really cool title, Complex Quantum Cognitive Simulation, okay? And this is like, now simply said, sometimes, of course, we're all in quantum computing, and we like to market quantum computing, and we say that weather forecasting is one of these things that we could disrupt. And it's important to say in very simple manners that we're not just going to take the whole problem of weather forecasting end to end and just, run it on a quantum processor and get results, right? It is going to be a highly complex, highly distributed, multi-technology, multidisciplinary workflow that will include also quantum processors, among many other things. And so if all of these industries benefited from heterogeneous infrastructures for years, both in high-performance computing and in the cloud, right? So I think that what we owe them is a heterogeneous quantum solution as well. both for high-performance computing and infrastructures and cloud, right? And this is the main takeaway of this talk. By the way, I'm glad to see that of many other talks in this year's Q2B. And so this is really crucial going forward. So how do we look at that from a technical perspective? So in order to get a bit more technical, we actually need to remind ourselves once again of how the stack looks like. And the stack is, of course, it always begins with the most important part, which is the quantum processors, right? This is the most important part, the heart of the quantum computer where all the potential and magic is. However, in order to realize the potential of these quantum processors, the control layer is also very, very important, the control hardware and the control software. But then if we want to realize the potential of the entire computer, we should not stop there, right? We should not stop at the quantum computer layer, but we should go all the way and see the entire computing infrastructure in which it will be integrated. From the server infrastructure through workflow and job distribution and management, and all the way to the applications themselves. And in order for this integration to be effective, we need to do two main things. One is to have tight coupling between the quantum control layer and the high-level infrastructure. And the second, we need to efficiently expose the unique control requirements of quantum computers at high levels. Now, at Quantum Machines, what we focus on is the control layers. And our mission is to bring out the best of any QPU. I believe that's what we're doing successfully already, and achieve the fastest time to results. And the fastest time to results is, in this context, composed into two things. One is the fastest time to run your next gen algorithm, and the other is your fastest time to actually having practical quantum computers. So before we take a deeper dive, just a few sentences about us, about Quantum Machines. So we're the industry's biggest quantum control company with over 70 people, quantum passionate experts. We're the industry's most well-funded quantum control company with over $80 million in funding. We've pioneered real-time control, hybrid quantum classical capabilities, and multi-QPU support. And we are honored to have a massive customer base, including many of the leading players, many of them here, including corporates, startups, national labs, and academic institutions. Now let's take a closer look into the stack and how we go about it. So, so once again, we focus on quantum control, the hardware and the software. And what we offer to the world is the quantum orchestration platform. The quantum orchestration platform is aimed at running the most advanced quantum algorithms with the best performance and on any number of qubits. So of course, when we say these big words, the following question is, what is it? How does it look like, right? This is always the next question. So this is how it looks like. These are boxes. They go into 19-inch racks. And they are hardware and software, as I mentioned. The heart of this platform is, in fact, a processor. The pulse processor, a classical processor that we have developed from the ground up, which itself is responsible for real-time sequencing of quantum algorithms. But on the other end, what we need is an analog front end that will directly communicate with the qubits. So on the one hand, you have digital processors, classical processors, that orchestrate the algorithm in real time. They send digital pulses, but then these needs to be translated into the language that quantum processors speak, which is analog language. For that, we have analog front ends. But on top of that, of course, we have a whole layer which has to address the needs to integrate these systems into greater infrastructures. So what does that include? That includes workflow management, co-processors, stream processing, networking, error correction, storage, and caching, and actually the list goes on. Some of those were actually elaborated in Jonathan's talk yesterday, and some will be elaborated in another talk that we'll have tomorrow. I'll give the details at the end. So how do you speak to this system? So it can do all these wonderful things, but you need to talk to it. And you talk to it through a language, which is Qua. Qua is a pulse-level language. I feel confident saying that it's the most comprehensive pulse-level language out there. And you can speak to these machines through QA. You can send them jobs which go from calibrations to QA/OA through error correction protocols, and so on and so forth. But you can also use your favorite language, for example, OpenQASM3, which is now embraced by many as a standard for an intermediate representation for quantum computers. And of course, we embrace it as well. So let's take a deeper dive into some of these elements because it's pretty important in order to understand the whole quantum computer. So the Pulse processor is a multi-core processor which does the real-time multi-core quantum algorithm orchestration. And it takes the real-time hybrid quantum classical to an unmatched level. And some of these, we have quite a few examples for that. Some of those will be given tomorrow in Jonathan's talk about quantum error correction. It also performs the most complex quantum algorithms and experiments in record time. So now we have a new measure for actually for runtimes of quantum computers, CLOPS, which was introduced recently by IBM, and also we embrace. And it is also massively scalable, covers easily all QPUs out there. It's scalable because it's a multi-core processor, but then can be cascaded to having multi-processor processors working all together. The second very important component is QA. I believe that QA is the most commonly used pulse-level language. I don't have the data for that, but that's what I believe. It's employed by hundreds of physicists and engineers across companies, universities, and government labs to program processors based on superconducting qubits, trapped ions, neutral atoms, and of course other platforms which are more niche but could be much bigger in the future. And the last important component, last but not least, is of course the analog front-end, which is a massively scalable analog front-end. Again, can cover all QPUs out there, highly modular as well, and supports multiple different quantum architectures. So fundamentally, the quantum orchestration platform is the foundation towards practical quantum computers across all different types of qubits. And our key takeaways for this talk, and actually I believe for this Q2B this year, is that embracing quantum's role within a heterogeneous environment is itself key to its ongoing development by the community, by the enterprises, by the end users. That it is only the effective integration that will have vast implications on the control and integration layers in both the hardware and the software, and that we are committed to continue and pioneer the optimal control of quantum computers to provide a foundation to the realization of practical quantum computers. Thank you.
He can do it. He can.
And maybe the last note is that I'm happy to invite you all to our talk. So the first talk was given yesterday, but it's going to be available online. So I highly recommend it, given by Jonathan. And tomorrow another talk by Jonathan about flexible quantum error correction with the quantum orchestration platform. So I think you'll be amazed to what extent quantum error correction protocols can actually be run already today. Yep. Happy to take any questions.
And so my question is, what kind of residual error level is acceptable for practical future computation? Is it 1 part in a million, 1 part in a billion, or 1 in 10 to the power 20?
So actually, I'm not an expert exactly in that, so I won't be able to I believe, to answer this question well. Yeah.
All right.
Chip?
For sure. I mean, not necessarily in a single chip, but in multiple chips, of course, for sure. This is even expected. Yeah.
For a chip of the nature you have there, how many quantum channels, how many qubits do you foresee being able to multiplex into a single chip? How should we think about that level of scaling out?
Okay, that's a great question. So the first answer is that this really, really depends on the quantum processor that is being controlled. So for For superconducting qubits, I mean, we can, at this stage, we can easily talk about 20, for example. And by several techniques, we can go even farther. For chips, for processors with trapped atoms, you can go even way more. So that really depends on the technique on the underlying quantum processor. Yeah. And that was for a single processor, if I understood correctly, right? For a single pulse processor. But then you can go farther with several techniques if you, of course, if you combine many of them. Yeah.
Who are the potential users of a pulse level programming language, and also who are the potential users of gate level languages?
Okay, great question. So these days, the users of pulse level languages are mostly the physicists and engineers that develop the quantum computers, right? These are the main users for those languages. Then for the gate level languages, these are mostly the end users of the quantum computers, right? However, we believe that on the long run, of course, the end users will want some exposure to the pulse level language as well, whether it is for calibration reasons or for optimization of their algorithms.
All right. Thank you very much. Thanks, Itamar.
Thank you.
Thank you. Can I have this? Okay, good.